Hello, YouTube. I actually checked to make sure I included the equations in this one before just going forward and doing it. And I hadn't, so good thing. Today, in particular, we're going to be talking about potential energy graphs. This is a subject that I think is really cool and a problem solving method that I think is really cool, but also really heavily based on intuition. So, frankly, it's very difficult to explain. Please feel free to ask follow up questions on this one. I'd love to know what parts you want more of an explanation on so that makes more sense. Um, so, in particular, we're going to be looking at graphs of potential energy versus position, or I guess position versus potential energy, and then using those to model how the object's going to move, because there's some neat stuff you can do with that. Um, Ideally, end of the day, you should be able to identify if a force is conservative, and that's going to be sort of how you figure out whether or not to call something potential energy. Using that, you can use the relationship between potential energy and forces to figure out what the force on an object is going to be, or interpret the potential energy graph of an object to figure out how an object will move. In particular, conservative forces. Conservative forces are any force that will always do zero work if the object starts and ends in the same place. So that means if you like begin here and you lift something. So for example, gravity. If you start here and you lift something up to here, and then you bring it over to here, and then you bring it back down to here, and maybe you dip a little under, and then you come back up. The work that gravity will do in that case will always be zero. If the object is moving at the beginning of that process or end of that process, it won't be because of gravity. Um, Similarly, if you like have an object on a hill and it slides down the hill and then it goes up a half pipe to the other side of the hill, in order to get back up to the same height, gravity will do a total net work of zero. And that's sort of what makes gravity a conservative force and what makes it useful to track gravity and potential energy as though they're sort of a thing that exists. Because honestly, like, potential energy is sort of a weird concept. The object doesn't super have energy. Um, as like, I guess, a quick way to prove that, let's say that we start with an object at a location, we bring it up to here. Um, the force of gravity will always go down. So regardless of what path we take, the component of the displacement for the object from here to here will always be its height, and the force of gravity will always be mg. So mgh will always be the work that gravity does regardless of the path we take. So regardless if we go like that, regardless if we go like this, regardless if we go like this, in order to get up to this height, we'll do this much work. To go from here to here, the work that gravity does will always be zero because the angle between will always be zero. So if we bring our object to here, it'll always do zero work. If we bring our object back down to the same location, again path independent, we'll do a work of negative mgh because this time gravity will go parallel to that height component of whatever motion we have. And then we can bring ourselves back to the starting location. I should probably have arrows on these. We should bring ourselves back to the starting location, doing no work for the same reason that traveling sideways across the height did no work. And in that case, we'll have positive mgh and negative mgh to go up and down back to the same place. That same logic will hold if we go down then up. And so no matter what path we take, no matter what place we go to, gravity will never be able to do a net work on an object brought back to that same starting location. Hence, conservative force. Springs will actually wind up being the same type of thing. When you bring an object from here to here with a spring attached to it, that spring will do negative work trying to pull the thing back, and it will do negative work equal to negative 1/2 kx squared. So it'll be taking away energy from the object by that amount. But then when you bring it back from here to here, it'll do the same amount of work, but this time positive, 1/2 kx squared. And so when you go on that closed loop, the spring does no work. The reason why that happens in both of these cases is because the force from the object is always pointed back towards one location. In this case with the spring, it was always pointed back towards the middle. And even if we had brought it over here, it would always be pointed back towards the middle. And so any energy that we gained by bringing it, any negative work that the spring does by bringing it away from that location will be undone by the positive work that the spring will do bringing it back towards that location. For gravity, because it's always just pointed down, any positive work that gravity does bringing the object back down, this actually should have been negative and this one should have been positive. Any positive work that the object, gravity does bringing that thing back down will be undone by the negative work that gravity does when you bring the object up. If you were being hyper-technical about it, you could say that a force is conservative if the closed loop line integral from point A to point B of that force in terms of position is equal to 0. You won't have to do this for the AP exam. I think I might have had to do it for college, but like that's just a little bit more technical than you have to be as far as the concepts are concerned. This is just sort of if you wanted to explicitly prove it. And what's neat about that is that that makes it path independent. It won't matter how you get from point A to point B, because if you overshot and then came back, the net work you did by that overshooting and then returning is always 0. So getting between point A and point B will always, always, always require the same amount of work. And so it will always, always, always give the object or take from the object the same amount of kinetic energy. And so you can start conceptualizing it as a second type of energy because it kind of just functions like it's energy stored within the positional relationship between this thing that's providing this force, either the spring or gravity or whatever else, and the object. So this allows for the conservation of potential and kinetic energy, and this is why potential energy is a useful concept, because you can freely consider the energy lost by fighting against gravity to be energy that you will then be able to gain if you let it return to its initial position. This is significant and special and separate from stuff like friction, because if we look at how friction functions, if I have an object and I start here with friction and I drag the object to here, the object's displacement vector will look like that, but the force on the object from friction will be backwards. So we'll have a work for this section 1 of negative x times our force of friction. But if we drag it back, friction will actually be pointing to the right. And so unlike that other stuff where the force was always pointing in the same direction, this one's actually not going to do that. And so what'll happen is work 2 will actually also equal negative x times the force of friction. And so if we take x to be our distance away from the starting point, the work that's done by friction total in order to go along this closed loop will not be equal to 0. It'll actually be equal to the combined distance, the force of friction times the combined distance that we wind up traveling, but negative. And so it's not like gravity, or it's not like the spring, because we won't get that kinetic energy back by undoing our movement. That kinetic energy is just gone and then some. And by gone, I mean dissipated to the environment as heat. But like if we're thinking about a one object system, it doesn't really work. Or in the case of things where you're tracking potential energy from gravity, a two object system of like the object and the Earth. They like that phrasing sometimes. when we're going over like individual problems, it'll probably come up more and we can talk about it then. Which is the only reason I bring it up. I actually don't like bothering. So, if we want to talk about potential energy graphs, we then have to talk about a specific relationship between potential energy and force. In particular, because you can think of the potential energy stored up as sort of this, the work that the thing did, and then the amount of energy it'll give you back if you undo that work. Because work is equal to force times distance, and we're talking about the amount that we would get by undoing, negativing the work. Potential energy is equal to negative work done by the conservative force. So if you rearrange that and take a derivative, this is sort of a slapdash derivation of this equation, you'll get that the force on an object from a conservative force will be equal to the negative derivative of the potential energy of that object with respect to position. We're going to do a super quick example with this. We don't honestly super like have to, but we're gonna. And then we're going to talk about the real thing that this tends to get used for, which is potential energy graphs. And that's the part that's like really cool and mostly based on intuition. So if we've got a semicircular hill of radius r, and we've got an object that is at some x location along it, the question is, how can we find the force on the object at any given x position? And we could do this pretty straightforwardly by like using the normal force on the object and the component of gravity. And so if we're doing that, like I think we've actually done this for a different problem already. We'll have an angle, we'll have that this is r, we'll have that this is h, and we can say that because we'll have mg times the cosine of theta as our force going down that component of the hill. And as I've drawn it, that'll be going in the positive x direction. Yep, mg cosine theta, and that'll equal our force in the x direction. And we can go ahead and say, I'm going to rewrite that because that m is mixed with an f and it's awful. And we can say that our height is equal to the square root of r squared plus h squared, or sorry, r squared minus h squared, x squared, geez, Pythagorean theorem's hard. And then we can say that our cosine of theta is equal to x over r. We can come over here and say mg x over r is equal to our net force in terms of x. So now we've got a function of force in terms of position. But I do want to try it a second way using energy. And so using energy, what we can say is that our potential energy is equal to mgh. And h is equal to the square root of r squared minus x squared. Did I do this wrong? Yes, this actually should be sine theta, not cosine theta. So this is h over r, so this is the root of r squared minus x squared. Sorry about that. The force going down a hill is mg sine theta instead of mg cosine theta. And this is why memorizing correctly is important. All right, so mgh is going to be our potential energy, and all we have to do is take the derivative of this thing with respect to position, and that'll give us an equation for our force. So the derivative with respect to position is going to be, we'll have to do chain rule, so 1 over r squared root r squared minus x squared, and then mg, and then negative 1/2, and then we'll have, so we drop our power of 1/2, and then we drop the power by 1/2, and then we take the derivative thing inside, so x squared, derivative of this is 0, derivative of this is going to be negative, so we've got a negative derivative, so negative, negative, x squared, take the derivative of x squared is going to be 2, that half drops with that 2, and sort of in a similar amount of time, this is just a second way to do the same thing, we've got mgx over r squared minus x squared, which is a little bit different from what we had using the forces approach on the surface, but it's also the kind of thing where there's some weird trig identities, or not trig identities, there's some weird identities we could use to probably relate the two. Should I probably redo this video? Yes. Will I probably redo this video? No. I am fairly certain that those two things should be equivalents to each other. I'm blanking a little bit on why it doesn't look like they are. But I'm going to move on. So it's just two ways to figure it out. Here's the meat, which are the position graphs. So in particular, when you have a position versus potential energy graph, the derivative will give you the negative force. And what's cool about that is that if you look at this graph, I think red-green colorblind is the thing. Let's try white. This white line here is going to give me the negative derivative, is the negative of the force. This slope is negative, so our object would get pushed backwards if it was the positive derivative, but because it's the negative derivative, our object gets pushed backwards. The steeper the thing is, the more the object gets pushed forwards. And so what's neat about this, the steeper the object gets pushed in the direction that goes away from the line of the graph. So in this case, our graph looks like this. Because our derivative goes like this, our negative derivative would be very strong in that direction. So in a very steep thing, our object is getting pushed that way very rapidly. And in a very shallow location, our object is not really getting pushed side to side at all. This is really neat for a few different ways. The first of which is that means you can conceptualize your potential energy graph as effectively showing you how the object will get pushed. And because it's showing you how the object will get pushed, and a hill, the angle of the hill is also something that shows you how hard the object will get pushed by gravity in the exact same way. What's really neat about this is that you can then treat it like and conceptually figure out what will happen to the object by thinking of an object on a potential energy graph as a ball on a hill. If I take a little ball and I drop it on a hill that looks like this graph, what that ball will do is roll down to here and then get back up to this height and roll back and forth between those two things. Even if what this potential energy graph is showing you isn't a literal hill, you can visualize and can predict what will happen as though it were literally just a picture of a hill, which to me is so cool because it's this like really abstract math thing that functions as if it's like a picture that you can just visualize this real thing and use that as a problem solving approach. So like if I have an object that starts here that object that starts here will have a potential energy at rest. That object will have a potential energy and a mechanical energy that goes up to that dotted line. And so the object would be able to make it far enough to go over this hill, but wouldn't be able to make it far enough to go over this location because of that. And it would just sort of alternate back and forth between those things. So for that way, you can use it to sort of figure out if the object would be trapped in an energy well, like this red one would, because it wouldn't be able to get out of the energy well that'll function as though it's a literal like half pipe or a well on a hill. Whereas if you've got this other situation where you've got enough energy, you can get out of the energy well and not be trapped in the energy well, because you'll be able to roll up and over the sides of the well. Another way that you could have it not be trapped in the energy well is if instead of starting from rest here, you started with some kinetic energy. If you started with some kinetic energy, then I'm going to graph this in pink, you might have enough mechanical energy to get out. So if you know that this pink barrier represents how much mechanical energy the object has, then you can look at a graph of potential energy for the object and be like, well, if the object's traveling to the left, this is the highest or furthest to the left it'll be able to go, because that's the point, the x position. So like our left x max will be this place here where our mechanical energy intersects with our line, because this is basically saying, well, we don't have enough mechanical energy to go higher than this point because it would require more energy than we have. But if I look to the right, the object would be able to just sort of go off of here and be totally fine escaping in that direction because we have enough mechanical energy that we would still have kinetic energy left over when we needed this much potential energy taken away. So that's just like a really neat way you can use potential energy graphs. I should also talk about stable equilibriums versus unstable equilibriums, which are really easy to visualize on a potential energy graph. So if you have a stable equilibrium, what will happen is you'll have force pushing you back towards the middle. And if you have a force pushing you back towards the middle, then if you had an object here and you gave it a little push so that it was here now, the force would go the opposite of the derivative, so the force would go back here. And so that object would get pushed back here until it reached this point, at which point it would go a little bit over and then get pushed back here. And so you've got this situation where even if you push it a little bit, the object will get pushed back towards the middle and it'll stay in basically the same spot. Now at this point, the force is equal to 0 because it's a flat point on the line, so our derivative is 0. So this is a point where if you place an object there, it'll stay there, and if you give it a slight perturbation, if you give it a little tap, it will come back to the same place. And so this one is a stable equilibrium. It's an equilibrium because the net force is 0, so it won't move, and it's a stable equilibrium because it'll stay there even if you try to make it leave. If we look at this second point, for this second point, if I put the ball here and I give it a little tap and now it's over here, the derivative here is 0. But when I give it a perturbation, the force on it's going to go to the left, pulling it away from that point, and it's just going to start rolling down the hill. And so this location would be an unstable equilibrium instead. So, and that's like really useful for why figuring out that like you can use this to figure out whether or not an object is easy to keep balanced in a certain configuration. You can use this to figure out whether or not you would expect something to like stay if you let it go on a hill. You can use it to figure out whether or not like a spring will hold an object in one spot, or if the spring will like make it go nuts. Like I don't know. It's nerdy, and it's based around like using math visualization and thinking that that's cool. But I just like think it's a really neat concept. Again, more based around intuition than anything else. So, this one's certainly gone on long enough. If you got questions, let me know. I think the big takeaways from it should be stable equilibriums versus unstable equilibriums on a potential energy graph, using the mechanical energy on a potential energy graph as a way to figure out whether or not an object would be able to go in one direction or another, and where its maximum positions in either direction would lie. And knowing that you can take a derivative of a function of the potential energy of an object in terms of its x location. Oh, that's why I had the problem. I did the for the last one, I did it. No, I turned it into EU in terms of x before I took the derivative. Anyway, you need to take the derivative of the object with respect the potential energy of the object with respect to position, and that'll give you your potential energy. So, sorry, that'll give you your force on the object. That's in the x direction, your force on the object in the x direction. So what I found there was actually the x component of that force, not the net force on the object, I believe. Anyway, sorry, that thing's gonna bug me for a while. I hope you have a good night. Goodbye, YouTube.